ladies and gentlemen, let's look at this problem step by step. Now, gentlemen, quiet down. Stop touching each other, please.
Oh my gosh.
All right. You want me to send you back to middle school to be separated? I can. This is a college class.
I'm not listening.
We'll go outside. All right, let's have some fun on this one. You'll notice this problem is written differently than some of the other ones. That's intentional. The AP test loves to do this. Loves to do this. So, you have to always think about what it's asking you and how it's asking you to go about it. So in this one, it's a good thought problem to go through and to solve it. You've got solid sodium carbonate. It is added in order to precipitate all of the silver ions from a solution of silver nitrate. Some of you said, okay, we got sodium chromate added to silver. Unfortunately, that's not what's going on. What's happening, though, is the sodium chromate is being added to a solution that contains silver ions, silver nitrate. Silver chromate is the precipitate, so we know that should be the product and should be a solid as well. So writing the complete balanced reaction equation and the reaction type for this one here, you've got the sodium chromate being added to the silver nitrate, aqueous producing the silver chromate and the sodium nitrate, which is the one that was not given to us. Yes, sir?
Whenever we write a complete balanced chemical equation, do we need to have the state of the substances always?
You do not lose points on the AP test unless it asks specifically for a solid. So you would not lose points if you didn't have them for most problems, but it is very advisable for your life in general. Yeah, if you're looking at, especially if you, it makes it easier because it tells you if it's a precipitate or not, whether it's a solid or not. But on a question like this, they would not take away a point. It would probably only be worth 1 point anyway. So you got all this stuff, or 2 points, 1 or 2 points. One for the substances, one for the coefficients. Usually the case. Then you got double replacement. It's a type of reaction. The sodium and the silver are switching places. Is the way of thinking about that. Yes?
We have to have the S and the AQ.
As I said, the AP exam will not take a point off on that usually. But since it is a precipitation reaction, I do expect you to have at least the S here for that. The AQs are good chemistry, but the question's usually only worth 1 or 2 points at the most, and so if they took off for that, people will be getting zeros all the time. So with this information, to get the percent composition of the silver, come on, here we go. You take the mass of the silver divided by the mass of the silver chromate times 100. You've got, again, 2 moles of the silver there. So that's why it would be 65.033% silver. Yes, sir?
Since the oxygen's only has 4 sig figs, shouldn't it only have 4 sig figs as well? Because on our chart, the oxygen only has 4 sig figs.
When you're adding them together, it stays to the hundredths place, so that's why the 331.74 would be accurate in the addition, and that's why it gives it 5 from 4 to 5 because of that addition. Yeah. But then you divide, but this one on the top has 1, 2, 3, 4, 5 sig figs. This one has 1, 2, 3, 4, 5 sig figs. That's a precise number. So 5 on top of 5 gives you 5 at the end. So it doesn't limit you. Yeah. Yes, you always want to include sig figs for the answers. I don't think this is one where they'll be looking just for sig figs, but once again, it depends on the problem. But if you don't use sig figs all the time, you'll get to a problem where you will need them and you'll lose lots of points when you should have used them. So Just use them all the time as good habit and good chemistry. And in college, they go like this to this. They go 65, wrong. No ifs, ands, and buts. There's no like, oh, let's give them partial credit just because they look nice. And they have a pretty picture of all the work they did. Sometimes. Depends on your teacher, of course. You might get the really teacher that wants to spend extra time going through your individual problems, but most of the time, chemists are looking for what's the answer, let's go, move on. So I just want to give you a heads up, that's to be expected, unfortunately or fortunately. Now for part D, the reaction could be rewritten like this if you wanted to. This may make it easier to see what is happening. So your two silvers plus the chromates are making your silver chromate. This is just removing the spectator ions from the equation. You've got 0.650 liters of the silver nitrate, 0.100 moles per liter, or that's the molarity. This tells you how many moles of silver nitrate you started with. The ratio between silver nitrate and silver is 1 to 1. So you start with 0.00650 moles of silver. So this is the amount of silver you start with. You convert that into amount of chromate. And then you convert the chromate into sodium chromate, and then use the molar mass of sodium chromate. So this is one way to work the problem using the net ionic equation. You could use the full equation as well and get the same answer. So many of these conversion factors are from the ratio, from the balanced chemical equation. This one here is your molarity. This one here is your volume. And then this here is the molar mass, happens to be of the sodium chromate, which is what you were trying to get the mass of. Because you have 3 significant figures in the volume initially and 3 in the molarity, that limits your answer to 3 significant figures here at the end. All right, ladies and gentlemen, again, this is one way of solving it. Here's another way of viewing it. Okay, you've got your equation. Underneath your equation, you write down what you have, which in this case was molarity in milliliters, right? So use those two to find the moles of the silver nitrate. Convert that into moles of the sodium carbonate, and then back into grams of the sodium carbonate, and that will give you your answer in terms of what is needed to react with the silver nitrate. So this is the way I see the problem, but if you have a net ionic equation and you have to use it, you can use that to help you out with the ratios. So the ratio in this case, it's going from 2 to 1. So when we set this up, we've got our molarity, which is here, our volume, which is here, same setup. Okay, and then we kind of can skip some of these things here. Well, can't skip that one. We can skip this part here. But a couple ways of solving the same problem. Any questions, clarifications on this? Okay, being able to follow both types of problems is good. Not always necessary. Just getting the answer is what we're going for. So how you approach it is up to you. So let's look at a separate type of problem. This here is with a magnesium. Magnesium reacts with a certain element to form a compound with the general formula MgX. So what would be the most likely formula for the compound formed between potassium and element X? What do you think? All right, so if we look at this problem, it's got a lot of words. Yes, sir? P2X, close, but not full. Unfortunately, yeah, P is phosphorus. So K would be the only possible answer there. But you would have the ratio right. Ratio is right. Good job on the ratio. I don't know if I'll give you partial credit, but the ratio is right. So K2X is the answer. This problem takes about, 10 seconds. So the previous problem took maybe 10 minutes. This one takes 10 seconds.
So like the
One's on the bottom, multiple polyatomics, single ones will be transition rounds, and ones will be K wants to have one positive charge and he has two positives. So if they're connected with the same thing, then that ratio works. All right. Problem number 7. Please answer number 7 at this time. This should take about 1 minute. All right, let's look at number 7 here, at least how to think about the problem and then how to get our answer. So we've got 2 isotopes of boron. Okay, you got boron 10, which has a mass of 10.013 AMUs and the percent abundance of 19.61%. The other isotope, which we don't know what it is, since it's only 2 isotopes, the total percent abundance has to equal 100 of the 2 isotopes. So you take the 19.61, 100 minus the 19.61, and that gives you the percent abundance here. Once you have the percent abundance here of this one here, you can find out the mass of the additional isotope. So boron's average atomic mass is 10.81. So 10.81 equals the percentage, the 0.1961, 10.013 given to us. This was the unknown percentage that we calculated, and the x's are unknown. So with boron being 10.81, that's 11.00 AMU for this second isotope. That would be the answer. So we got this off the periodic table here. And this was the percentage converted to a decimal. And this one is the given AMU of boron 10. So this one would be known as boron 11. Yes, sir? It can be on the test, absolutely. I've seen many chemists that like to do isotope calculation type problems. Yep. Yep. So if you set this up with your 10.81 here, that's the mass of all the isotopes, the average atomic mass. Okay, you can solve backwards to find what this number here would be. All right, the last one. I'm sorry, number 8, pardon me, not the last one, but number 8 is Djenkolic acid. I'd like you to find the empirical formula for Djenkolic acid, please. Ladies and gentlemen, what do we think the formula for this acid is going to be? Raise your hand, please, because I can't hear so good anymore. Yeah.
C7H14N2O4S2.
C7H14N2. Oh, what?
O4S2.
S2? Like that? Okay. Any other possible answers? Support it? How many people support that long answer? Alright. So let's look at this problem. What's the first thing you have to do?
Find the moles of each substance.
Moles. So what do you have to assume? Alright, so you assume 100 grams. Then you find the moles of each. Then what do? Divide each by the smallest one. So that's called a comparison or whatever you want to call it. You get your ratios. Okay? And then once you got your ratios, you got to make sure that they are what type of numbers? Whole number ratios. So if you need to multiply at that point, you can. We wanted to get the empirical formula for this acid. So we're not given any other information about molecular formula or molar mass. So find the moles of each element. Given the percentages, assume 100 grams. These are our moles we got. Smallest one looks like the nitrogen and the sulfur, which should be the same amounts, which they are on the formula, which is good. Simplest mole ratio, you divide them all by the smallest number. We get 7, 1, 2, and 1. 3.5 has to be doubled, so the whole thing has to be doubled, giving us our Formula C7H14N2O4S2.
Can you go back for a second?
Yeah.
Thank you.
Now, this here would be an acceptable answer as an empirical formula. Okay, you could have also written, if you wanted to include the hypothetical n. You could have included the hypothetical n here as well. That would have been okay as well. But this is usually what most people put for their answer there for the empirical formula. So they're both the same thing.